maybe you're way ahead of me. But I want a derivative. Did you guys do this? What did you get for a first derivative?
2x.
2x cubed?
Yeah, 2x cubed
plus
6x squared.
6x squared. Now, I need to work on this first derivative, but let me, while I'm at it here, let me just jump to the second derivative while I'm at it, because I'm going to need that eventually. The second derivative? 6x squared.
Yeah, 6x squared
12x.
Plus 12x. Okay, cool. All right, now here's the game. The game is I want to know when this first derivative equals 0, or where it's undefined. But let me ask you, when is it undefined? Never. Okay, so when is it 0? Well, here we go. Maybe factor out a 2x squared. You have to factor it. That leaves me an x plus 3, I think. Careful, you know, your algebra is what gets you sometimes. So now I'm setting this equal to 0. I know how to do this algebra. This equals 0 when this equals 0, which is when x is 0. And it also equals 0 when this equals 0, which is when x is negative 3. Sorry. Negative 3. Are you guys okay?
Those are your critical.
Those are my critical numbers. I label them. Again, I'd encourage you to work like me. I'd encourage you to be little mini me's, but you also have your own individuality, I suppose. But I got my critical numbers. Let's go ahead and test them. I'm going to put them on a number line. I'm going to label the number line F prime. And I'm putting these guys on here. 0, big and bold, and negative 3, kind of big and bold, because those are my critical numbers. And then I test in between. And if you screw up the testing, that really kind of messes up your graph. Like if if you find out it's decreasing when it's really increasing, I mean, that's bad. That'll kind of mess with your head. Because it just won't look, something won't be right. So anyway, this testing part's important to get it right. Here we go. I'll pick a number out here, like 1, and plug it into the derivative, right? I'm testing to see whether the derivative is positive or negative. If I plug a 1 in there, I can easily see it's positive, don't you?
Right.
So this whole region's positive. So this is increasing. Let's check this region, and I can test any number I want. I'll pick a little negative 1, and I'll plug it in here. When I plug it in here, it's positive. When I plug it in here, it's positive. So I think that's positive.
Yeah.
So that's positive. That's kind of interesting. A lot of the problems we did last week, they would always switch. They'd go from positive to negative to positive to negative. They're not guaranteed to switch. That's why you test them all the damn time. So this didn't switch. This is still increasing. I don't know about concavity yet. Now let's test something out here. Negative 4?
Yeah.
Negative 5? Whatever. Negative 4. You know, when you square it, this is positive, but it's going to be multiplied by a negative 1 when you plug a negative 4 in here. This is what I'm doing. Negative 4 plus 3, that's negative, multiplied by something that's positive. A positive times a negative is negative. That's how I'm doing it.
Right.
So, cool. So it's decreasing. Well, guess what then? If it's decreasing and then increasing,
That's a min.
that's a min. And I mean this guy right here. He's a min. Awesome. This one's not. I mean, it's increasing, then it's still increasing. He's a neither. He's not a min or a max. He was a critical number, but he came out to be not a min or a max. You know what he is, though, too? He's a critical number. He's a place where the slope is 0. I mean, I'm going to go look at this graph real carefully in a minute, but how can you be a place where the slope is 0 but not be a min or a max? You got to be this. Are you following me? You're one of these places. Your slope is 0, but you're not a min or a max. You're one of these. You're increasing, and then you level off, but then you continue to increase. That's what that looks like when we get around to it. All right, well, let's work on our second derivative. I'm looking for inflection points, so I set it equal to 0. my second derivative, I set it equal to 0, I do this algebra, I factor out a 6x, you guys agree? Left with x plus 2, I set this all equal to 0, I get x equals 0, and I get x equals negative 2. Cool. I call those possible inflection points at this moment. I'm not real positive if they're inflection points or not until I test them. I put those on a number line. Underneath this number line, I label it f double prime, and I do this what I call a concavity test. Now, one of these points was a 0, the other one was a negative 2, and I should test the regions around it. I'm testing to see if the second derivative is positive or negative. That'll tell me that the function is concave up or concave down. All right, here we go, here we go. I'll pick a 1 out there. I'll pick a 1. I'll plug it in the second derivative. You know, I can plug it in here or here. I like it when it's factored. It's positive. It's positive, right? Concave up. Let's try a negative 1. I'm trying a little negative 1 right there. That's negative. That's positive. So a negative times a positive is, this is a little negative region here. It's concave down just in that little region. We'll try a negative 3 here. Negative 3 makes that negative 18. Negative. That's negative. A negative times a negative is a positive. So this is positive. So this is concave up. So at these places that I was investigating, it really did change concavity. It really did change concavity. So they really are inflection points. This is awesome, you guys. I think I want to sketch the graph now, if I can. But not only that, let me show you something. On a test or a quiz, then I think I would have, you know, this little chart listed for you here. Can you tell me the relative mins? Can you tell me the relative maxes? Mins, there could be more than one. Can you tell me the inflection points? And you can now. We could work on that. Let's see. What about for the relative min? For the relative min, we found one, right? X is negative 3. It'd be cool to find the y value. Let's just do that. How do I find the y value?
Plug in the f of x.
Plug it in the original function. All right. So now I'm just back to plotting points. Maybe your calculator can help you do this, you know. That's 81 over 2 plus negative 54. You know what happens when your teacher starts growling, right? Negative 27 halves?
Yeah.
Negative 27 halves. Okay, that's my y value. All right, what about a relative max? Sometimes I ask you for stuff and we don't have any. Don't leave it blank, because then I don't know what you know. Write the word none. There are none. So you knew what you were doing. Inflection points. Where are they? Oh, here they are. We found them. These are the x values. It's negative 2 comma something and 0 comma something. Let's plot those points. If I plug a 0 in the function, I get 0.
Oh, no, I'm sorry. I'm doing negative 2.
And if I plug a negative 2 in the function, I get 16 over 2 is 8. Minus the 16, I get a negative 8, huh? I get a negative 8. All right, this is awesome. This should all come together beautifully here. I'm going to plot these points. 0, 0. Negative 3 is right here. Negative 3, negative 13 and a half. That's what I'm going to call that. Negative 13 and a half. And negative 2, negative 8. Negative 2, negative 8. And now I should be able to draw this. Reading those number lines, draw this. Or if I typed it in my graphic calculator, I could see what it is. But I like to save that for suspense. I like to challenge myself. What am I doing? Starting way over here on the left, I'm decreasing. I'm decreasing. How am I decreasing?
Down.
Well, I'm decreasing, but I'm decreasing concave up. See, that's the phrase. You know, there's two ways to decrease. You can decrease concave down, or you can decrease concave up. You can decrease concave down, or you can decrease concave up. So I'm decreasing concave up. So that's way over here to the left. I'm decreasing concave up, I think, until I hit this -3 right here, right? All right, hold on. What happens after I hit -3? I start to increase. Thank you. I increase. By the way, I'm still concave up. I'm still concave up until I hit that -2. So here I go. I'm increasing, and I still have a little concave up bend to me. You see that? But when I hit that -2, what happens?
Concave down.
I'd switch to concave down just for a little while. By the way, I'm still increasing. I'm still increasing. I mean, but look at this. The concavity switch. Do y'all see that? That was my little concave down segment there. Then I hit that 0. What do I do now? I switch to concave up. What's funny is, I was about to try to decrease, and no, I'm supposed to keep increasing, remember? I'm supposed to keep increasing, but I do switch concavity. So I'm going to continue to increase, but I'm going to switch to concave up. Dude, this is beautiful. Look at that thing. It's beautiful. We analyze the hell out of it using the first and the second derivative, using what we call a first derivative test and a second derivative. No. That's not what this is called. A first derivative test and a concavity test. The second derivative test was something else. We talked about that last week. I didn't need it. I don't need it. I didn't need it on this one. All right, you guys. Listen, so we go to 4, 5. Are you guys all right? Hang on, any questions? You all right on this? I mean, it's a lot of work, but in a way, this was an easy one. I mean, the derivatives were easy, and setting them equal to 0 was pretty easy, right? Quick little factoring. I mean, there wasn't a lot of hard quadratic formula work or anything crazy here. So even the easy ones are a lot of work. I mean, it's a bunch of work. That's awesome, though. In 4, 5, it got a little funny. Friday, I did these limits that go to infinity. I'm not sure I even care about limits that go to infinity. I don't even know if that'll be on a quiz or a test. The connection I was trying to make, though, was when limits go to infinity, if they have an answer, they're a horizontal asymptote. I was trying to make the connections to a limit that's heads toward infinity is really kind of asking you, what's the horizontal asymptote? So to me, 4, 5 is sort of a section about reminding you about asymptotes, vertical asymptotes and horizontal asymptotes. Kind of a reference back to pre-calculus, but using a little limit idea to teach you about horizontal asymptotes using limits. So I'm moving past 4, 5. Where it shows up is in 4, 6 in a problem like this. Look at this. If I go to 4, 6, and to tell you the truth, I wanted to open this book. Hang on a second. This is my secret solutions manual. And I wanted to find a problem in 4, 6. Yeah. All right, you ready for this? So I just went to 4, 6, and I found this problem, number 5. Is that what I want to do? Sure. Number 5. All right, you ready? Here we go. The function is this. 3x over x squared minus 1. Okay, here, you know what we want again? We want a complete thorough analysis, please. A complete thorough and everything. That means you got to do everything. Now that, look, you know what that means? You got to do a derivative. Derivative is a quotient rule. Hold on. You can do quotient rules. You're smart. I know who you're. But then we need a second derivative. That's probably going to be another damn quotient rule. So when it starts to get very complicated, and for a test or a quiz, you know what I could do? I could just give you the derivatives. Yay. When it gets really, I mean, when, you know what I mean? Because what I'm really after is, can you analyze these derivatives? I feel like last chapter you proved to me you could do derivatives. You still got to do them when you need to, but one way to save a little time on a test question is if I give you the derivatives. So here I am. That's why I brought this solutions manual. I'm giving you these derivatives now. Here they are, all cleaned up. They're all cleaned up. Negative 3, x squared plus 1, x squared minus 1 squared. Negative 3, x squared plus 1, all over x squared minus 1 squared. That's the first derivative, all cleaned up. The second derivative is 6x, x squared plus 3. 6x, x squared plus 3, all over x squared minus 1 cubed, I think. Yeah. And there's no way to really just see that. Okay, the way to see it is go knock out a quotient rule, clean it all up, you'll end up here. Knock out another quotient rule, clean it all up, you'll end up here, you know. So, but giving them to you and making you analyze them is a decent question, I think. It saves you a little time. Now this time, watch this. I think I want you to sketch a graph. But I have some more questions. Listen, so I have these two added things here. Do you have any vertical asymptotes? Please list those. Do you have any horizontal asymptotes? We better please list those. Do we have any relative mins? Do we have any relative maxes? Do we have any inflection points? You guys okay? See, because I have a rational function, you know, a numerator and a denominator like that, that leads to asymptotes. And the asymptotes highly affect the graph, so I need to analyze these asymptotes. So let's see, do you remember how to find vertical asymptotes? How do you find vertical asymptotes? Vertical asymptotes occur when, basically when it's undefined. So when is it undefined?
At 1 and negative 1.
At 1 and negative 1. When you set this equal to 0, you get two answers, 1 and negative 1. When the denominator equals 0 in the original function, those are vertical asymptotes probably. You guys okay? I mean, it's been all of a sudden I'm reviewing asymptotes but we did a little bit of this in chapter 2, I think, and pre-calculus. So yeah, so do we have vertical? Yes, we do. X equals 1 and x equals negative 1. As a matter of fact, I'm going to put them on the damn graph. 1 is a vertical asymptote. Negative 1 is a vertical asymptote. All right, what else? What about a horizontal asymptote? Do you remember those rules? Good, it is 0, and it's horizontal. Technically, it's called y equals 0. How do we know it's 0? When the numerator has a lesser degree than the denominator, lesser power. When the numerator has a lesser power degree than the denominator, it's automatically y equals 0. You could say it's this. Remember, horizontal asymptote is this. What's the limit when x goes to infinity? Maybe that helps, maybe that hurts. I don't know if that helps you or hurts you, but the limit as x goes to infinity is infinity over infinity, but the denominator is infinity squared. The denominator blows up huge, so it goes to 0. The horizontal asymptote is y equals 0. There it is, y equals 0. What if this would have been a 3x squared? Now they have the same degree. Do you know what the rule is when they have the same degree? It's the ratio of the leading coefficients. Now, this is a different problem, I'm sorry. If I made that squared, they have the same coefficients, and now it's a, no, they have the same degree. As x goes to infinity, it goes to the ratio 3/1, and there's a horizontal asymptote at y equals 3, 3/1.
So the horizontal asymptote would be 3.
So the horizontal asymptote would be y equals 3.
Or y.
When they have the same degree. What made it be 0? Because it was a lesser degree on top. And so it goes to 0. By the way, that's the horizontal asymptote story. It's just those two examples. That's right. Cool. That's cool. That's it, right? There is a third example. What's the third deal? When the numerator has a higher degree. All right, well, guess it's not horizontal anymore. Now it's slanted or oblique. And I'm not a fan of those. I don't know. You might run into them in the homework, but I'm not interested. All right, so I had to remind you about asymptotes. And again, I sort of feel like that's what 4.5 was doing. And if I went over 4.5 quickly, it's because it was reminding you of asymptotes. But now here I am in 4.6 trying to do one of these problems. So I've analyzed the asymptotes. Let's look for mins and maxes. How do you find mins and maxes? You need critical numbers. That means you need the first derivative. Oh, there's the first derivative already done for us. Cool. Let me ask you this. When does this first derivative equal 0? When does it equal 0? When the numerator equals 0. When does that numerator equal 0? You can set this equal to 0, but maybe you realize that you move the 1 over and take the square root, and you're running into imaginary numbers. This never equals 0. So when does it equal 0? Never. Okay, when is it undefined? Oh, it's undefined at -1 and 1. Hey, maybe those are critical numbers, right? Because whenever the derivative is 0 or when the derivative is undefined, maybe those are critical numbers? Okay, argue with me though. I'm not always right.
You have to check the original function, don't you?
Yeah, right. Are these critical numbers? Hang on. Are they going to be mins and maxes? Are they critical numbers? What are they? Oh, they're asymptotes. Oh yeah, remember? These guys are undefined in the original function, and technically if they're undefined in the original function, they ain't critical numbers. So how many critical numbers did I just find? None. Well, then how do I do a first derivative test? Look, I want to do a first derivative test so damn bad. But I got no critical numbers to put on there. All right, listen to me. This is new. I got no critical numbers to put on there. That's okay. If I had some, I'd put them on there. But here's the other thing. I'm going to put this -1 and 1 on the number line. Listen, I know they're not critical numbers, right? We know they're not critical numbers. But they're natural places that break the graph. They're natural divisions of the graph. They break the graph. These asymptotes break the graph into 3 pieces. And I want to investigate what's happening in all 3 of those pieces. So I'm putting these guys on the number line, and I know they're not mins and maxes. I know they're not even critical numbers, but I'm going to test around them. It's very natural to test around them because they're god dang asymptotes. Now, you know, this test is not going to provide any mins and maxes, right? We already know there's no critical numbers. What will this test do for me then? If it won't provide mins and maxes, what will it do?
Show you where the graph looks like.
It'll tell me about increasing and decreasing. That's what it does. Yeah, let's do it. It tells me about increasing and decreasing. Let's start in the middle. Plug in a little 0, please, into the derivative. When you plug a 0 into the derivative, I think that numerator is negative. I think the denominator is positive. A negative over a positive is negative. Decreasing. Let's try this, a -2. You ready? In the derivative. I think that's positive, but multiplied by a negative is negative. Negative over, you know what? Whatever you do down here, you're squaring it. It's positive. So a negative over a positive is negative, so this is decreasing. Okay. What about over there? Positive 2. Positive 2. That's still negative with that numerator. That's still negative. This is still positive. So it's still negative. Okay. Well then, this graph is decreasing. In between those asymptotes. Look, over here on the left, it's decreasing. Right here in the middle, it's decreasing. Over here, it's decreasing. That's what I just learned. All right, let's look for inflection points. How do I find inflection points? Second derivative. Oh my gosh. All right. When does the second derivative equal 0? The numerator, please. When does 6x equal 0?
0.
When x is 0. Dude, that might be an inflection point. Right? Might be. What about this guy, x squared plus 3? When does that equal 0? Imaginary numbers? Right, never. Imaginary numbers, right? Because it's a plus 3. If it was a minus 3, we'd have some answers. Okay, cool. When does the denominator equal 0? Plus 1 and negative 1. Those are undefined. They're undefined in the original thing. I mean, they're those damn asymptotes again. If I'm going to analyze this graph, though, and analyze the concavity, I think I need the 0 on there. But I think I still need this damn 1 and negative 1. I'm sorry. I think I still need to test around these guys. I know they're asymptotes, but I need to test the concavity around those asymptotes.
Okay.
Good thing I did the derivatives for you, right? What did I do? I tried to do the derivatives for you to save you time. Still a hell of a long problem, you know? All right, here we go. We're getting there, though. I want to test this second derivative here. I'm looking to test concavity here. How about a negative 2? Right here, negative 2. That's negative, that's positive, that's positive. I think it's negative. Concave down. I'm talking quick now. What about a negative 1/2? I'm trying a negative 1/2 right there. Negative 1/2. That's positive, that's negative. That's negative, and it's being cubed, so it's negative. That's negative, I think it's positive. That's concave up right there. How about a positive 1/2? A positive 1/2. That's positive, but this is negative, and it's cubed, so it's negative. So that's negative. Concave down. What about a 2? Positive, it's positive. It's concave up. Hey, this thing's changing concavity quite a bit. It's changing concavity quite a bit. Wherever it changes concavity is an inflection point, which makes me think, oh, there's an inflection point, there's an inflection point, there's an inflection point. But wait a minute. We know that that negative 1 and that 1 aren't really inflection points. They're those asymptotes, right? They're not points. Thank you. You just got to keep that in mind. They're not really points. I tested around them. They're asymptotes, but they're not really inflection points. They're vertical asymptotes is what they are. But this guy is a real deal inflection point. We did find one here. Hey, let's go over here to what we're filling in here. So I think I found an inflection point. The x value is 0. How do I find the y value? Plug it in the original function. If you plug a 0 in the original function, you get 0. Hey, what about these mins and maxes we were searching for? That was in the first. There are none. Remember, there were no critical numbers. Really, there were no critical numbers. I put the asymptotes up there. But anyway, there's none. So we need a none here. We need a none here. I do have this one important point, 0, 0. All right, again, if you have your graphing calculator, you could see this picture. If you don't, you could wait and try to draw it yourself. Holy shit. I got to read this and draw it myself. You ready? Starting on the left, what's going on? Decreasing.
Concave down.
Concave down. Dude, when you're over here on the left, and these asymptotes are here as a guide, The only way to decrease concave down is like this. I mean, it's got to be living in this corner. With asymptotes like that, they're there for a reason. They guide the graph. I mean, it wouldn't be this. It doesn't make any sense. This asymptote's not here if this graph lives up here. You know what I'm saying? It's got to live down there. That's the only way it makes sense. I'll tell you what, let's go to the extreme right of this graph. If you go to the extreme right of this graph, what's it doing over here? Decreasing concave up. With these asymptotes as a guide, how do you decrease concave up? I think you do this, don't you? You're one of these.
Yep.
See, when you have asymptotes, that's how the graph, right? These graphs are kind of boomerang shaped. Somebody told me that once. They're kind of like these boomerangs that approach these asymptotes. All right, what about in the middle? In the middle, what's going on? Between -1 and 1, I should read this graph. Between -1 and 1, what is going on? It's decreasing. And it starts off concave up, but then it switches to concave down, but it's decreasing. Concave up and let me see here. With an asymptote there, it's got to be kind of decreasing. Concave up. It hits this, and then what?
It goes concave down.
It's still decreasing, huh?
Yep.
Still decreasing, concave down. That's good stuff. That's hard work. That's a lot of hard work. If I was you doing problems up in 4-6, I wouldn't do too many. I would do 3 or 4, get a good sample.
That's good.
Some students get trying to argue with me right here. They say, wait a minute, you crossed the horizontal asymptote. That's illegal. Well, guess what? It ain't illegal. You guys didn't try to argue with me. You're actually, vertical asymptotes are barriers you never cross. Horizontal asymptotes aren't really like that. You can cross a horizontal asymptote all the hell you want. You really can, as long as you're crossing it somewhere in here. When you start heading toward infinity, that's when a horizontal asymptote becomes an asymptote. So in the middle, a horizontal asymptote doesn't even act like an asymptote. But once you start heading toward infinity, it acts like an asymptote. It will not cross it. Once you head toward negative infinity, it acts like an asymptote. It will not cross it. So you got a little different rules, maybe.
Yeah.
Hey, thanks for working hard and listening to me. Catch up on some homework. I may move into some new stuff or answer questions Wednesday, I guess. Oh, wait.